Compression methods. Basic compression methods. Error-free compression methods. For many applications, this is the only acceptable manner, such as for documents, text, and computer programs. This is often used for images because they are already an approximation of reality, with the spatial and intensity quantization and errors in the projection system. It provides compression ratio between 2 and 10. Huffman coding. Huffman coding is an entropy encoding algorithm used for lossless data compression. The term refers to the use of a variable length code table for encoding a source symbol, such as a character in a file, where the variable length code table has been derived in a particular way based on the estimated probability of occurrence for each possible value of the source symbol. Take one example as shown on the screen. Step 1. Arrange symbols according to their probability values, larger probability to small values. Step 2. Then add least 2 probability values for source reduction. Step 3. Iterate step 2 until you get probability value 1. The assignment procedure to get code values can be tabularized as arithmetic coding. Arithmetic coding is a form of variable length entropy encoding. A string is converted to arithmetic encoding. Usually, characters are stored with few bits. Arithmetic coding encodes the entire message into a single number, a fraction n, where n lies between 0.0 and 1.0. The process of arithmetic coding and the related block diagram can now be seen. LZW coding. LZW, standing for Lempel, Ziv, and Weiss coding, assigns fixed-length code words to variable-length sequences of source symbols but requires no a priori knowledge of the probability of the source symbols. LZW was formulated in 1984. Error-free compression approach that also addresses spatial redundancies in an image. It assigns fixed-length code words to variable-length sequences of source symbols. It requires no prior knowledge of probability of occurrence of the symbols to be encoded. It is conceptually very simple. Initially, code books of dictionary containing the source symbols to be coded is constructed. For an 8-bit image, the first 256 words of dictionary are assigned to intensities 0, 1, 2, going up to 255. LZW is used in tagged image file format TIFF, graphic interchange format GIF, portable document format PDF. The tabularized procedure for LZW coding can be seen on the screen. Unique feature of LZW coding. Coding dictionary or coding book while data are being encoded. Bitplane coding. Another effective method to reduce interpixel redundancies. Images bitplanes are processed individually based on multi-level decomposing image into a series of binary images and compressing each binary using any binary compression method. Bitplane decomposition. Gray levels of an m-bit gray level image can be represented in the form of base 2 polynomial. A simple method of decomposing the image into a collection of binary image is to separate the m coefficients of the polynomial into m-1 bit planes. Disadvantages. Small changes in gray level can have significant impact on complexity of bit planes. For example, if two adjacent pixels have intensity of 127, that is 0, 1, 1, 1, 1, 1, 1, 1, and 128, 1, 0, 0, 0, 0, 0, 0, 0, every bit plane will contain a corresponding 0 to 1, 1 to 0 transition. Alternate decomposition approach reduces the effect of small gray level variations, requires the representation of an image into m-bit gray code. M-bit gray code G-1 ... G2, G1 to G0 can be computed from the equation shown on the screen. This code has a unique property in that successive code words differ by only 1 bit position. Small changes in gray level are less likely to affect all m-bit planes. Example 127, 11000000 and 128, 01000000. Run length coding. Standard compression approach method which is used for facts. The basic concept is to code each contiguous group of zeros and ones encountered in L to R scan of a row by its length and develop a convention for determining the value of run. The most common method for determining the value of run. Specify the value of first run of each row. To assume each row begins with a white run, whose run length may in fact be 0. Although run length coding method is in itself an effective method for image compression, additional compression method can be realized by variable length coding. Black and white run lengths may be coded separately using variable length codes. For example, if AJ represents a black run length of J, we can estimate its probability. The approximate run length of an image is HRL equals H0 plus H1 divided by L0 plus L1, where L0 and L1 denote average values of black and white run lengths. Above equation also provides the estimation of average number of bits per pixels required to run lengths in binary image. Predictive coding. For example, the predictor can be defined as the related block diagram is also seen. For the first m values, fn must be passed on. If m equals 1, we get the differential or previous pixel coding from the figure. For 2D images, the rows are consecutively placed in the model above. We could also use a pixel from the previous row. For example, p of x, y equals round a1 f of x, y minus 1 plus a2 f of x minus 1, y. To make e or x, y as small as possible. However, a good initiation will become more difficult then. Lossless predictive coding. The encoder expects a discrete sample of signal f of n. A predictor is applied and its output is rounded to the nearest integer, f of n. The error is estimated as E of n equals f of n minus f dash of n. The compressed stream consists of first sample and the errors encoded using variable length coding. The decoder uses the predictor and the error stream to reconstruct the original signal, f of n. Predictor is initialized using first sample. The received error is added to predicted list, as shown. Linear predictors usually have the form as shown. Original image view of the Earth, the prediction error and its histogram. The error is small in uniform regions, and it is large close to edges and sharp changes in pixel intensities. The block diagram for lossless predictive coding is now seen. In most cases, the prediction is formed by a linear combination of m previous pixels. That is, the equation takes the form. 1D linear predictive coding will appear as where m is the order of linear predictor. The first order linear predictor graph and the corresponding image are seen. Compression models. Models. A general system model for compression and decompression is: it is customary to use the names encoder and decoder, which have its roots in the field of information theory, rather than names as compressor and decompressor. If the transmission or storing channel is error-free, the channel encoder and decoder are omitted. Otherwise, extra data bits can be added to be able to detect, for example, parity cyclic redundancy checks, or correct error-correcting code for memory errors, often using special hardware. We shall not pay any more attention to encoders and decoders. With lossless compression, it holds that G of x, y equals f of x, y. A general model for source encoder is: the mapper transforms the data to a format suitable for reducing the interpixel redundancies. This step is generally irreversible and can reduce the amount of data. Used for run length encoding, but not in transformations to the Fourier or discrete cosines domains. The quantizer reduces the precision of the output of the mapper according to the determined reliability criteria. This especially reduces psychovisual redundancies and is irreversible. It is therefore only used for lossy compression. The symbol encoder makes a static or variable length of code to represent the quantizer's output. It reduces the coding redundancy and is reversible. A representation of the source decoder can be seen on the screen. The general model belonging to the source decoder is shown here. The inverse for the quantizer has been left out. The generation of information is modeled as a statistical process that can be measured in much the same manner as the intuition of information. An event E with the probability P of E has: if a source generates symbols AI with the probability of P of AI, then the average information per output is H of Z equals minus sigma P of AI log R P of AI, the insecurity of entropy of the source. This is maximal when every symbol has an equal probability, 1 by n. It indicates the minimal average length for R equals 2 in bits per symbol needed to code the symbols. Compression classification: lossy compression, lossless compression. Lossless compression. Lossless compression is used for legal and medical documents and computer programs. Exploits only code and interpixel redundancy. Lossy compression. Digital image and video where some errors or loss can be tolerated. Exploits both code and interpixel redundancy and also psychovisual perception properties. Error-free compression applications. Archive of medical or business documents, digital radiography, satellite imaging. Compression standards. Image compression standards. JPEG compression. Joint Photographic Expert Group, international standard established in the year 1992, works with color and grayscale images, that is, satellite and medical. Generation-based JPEG. First generation of JPEG uses DCT plus run-length Huffman entropy coding. Second generation of JPEG uses wavelet transform plus bitplane coding plus arithmetic entropy coding. JPEG encoding and decoding. Discrete cosine transform of each 8 by 8 pixel array function of x, y leads to T of f u, v. Quantization is done by using a constant or using a table. Zigzag scan to exploit redundancy. Differential pulse code modulation DPCM on the DC component and run length coding of the AC components. Entropy coding Huffman of the final output. Image perception. Source image is made up of one or more 2D matrices of values. 2D matrix is required to store the required set of 8-bit gray level values that represent the image. For the color image, if a CLUT is used, then a single matrix of value is required. If the image is represented in RGB format, then 3 matrices are required. If the YCRCB format is used, then the matrix size for the chrominance components is smaller than the Y matrix, reduced representation. Once the image format is selected, then the values in each matrix are compressed separately using the DCT. In order to make the transformation more efficient, a second step known as block preparation is carried out before DCT. In block preparation, each global matrix is divided into a set of smaller 8 by 8 submatrices, block, which are fed sequentially to the DCT. Once the source image format has been selected and prepared 4 alternative forms of representation, the set values in each matrix are compressed separately using the DCT. The values are first centered around 0 by subtracting 128 from each intensity/luminance value. Block preparation is necessary since computing the transformed value for each position in a matrix requires the values in all the locations to be processed. DCT, Discrete Cosine Transform. DCT converts the information contained in a block 8 by 8 of pixels from spatial domain to the frequency domain. A simple analogy can be, consider an unsorted list of 12 numbers between 0, such as 2, 3, 1, 2, 2, 0, 1, 1, 0, 1, 0, 0. Consider a transformation of the list involving two steps. Sort the list, count the frequency of occurrence of each of the numbers. Through this transformation, we lost the spatial information but captured the frequency information. There are other transformations which retain the spatial information, for example, Fourier transform, DCT, etc. Therefore, allowing us to move back and forth between spatial and frequency domains. Images are two-dimensional. How do we perform 2D DCT? Two series of 1D transform result in 2D transform illustrated in above figure. Consider each image is divided into 8 by 8 blocks. The 2D DCT is applied to each block image f of I, j, with the output being the DCT coefficients f of u, v by f of I, j for each block. If the input matrix is P of x, y and the transform matrix is f of u, v, for the 8 by 8 block is computed using the expression shown on screen. All 64 values in the input matrix f of I, j contribute to each entry in the transform matrix f of u, v. For u equals v equals 0, the two cosine terms are 0, and hence the value in the location f of 0, 0 of the transform matrix is simply a function of the summation of all the values in the input matrix. This is the mean of all 64 values in the matrix and is known as the DC coefficient. Since the values in all the other locations of the transform matrix have a frequency coefficient associated with them, they are known as the AC coefficients. Quantization. The quantization equation can now be seen on the screen. F of u, v represents the DCT coefficient. Q of u, v is a quantization matrix entry, and f cap of u, v represents a quantized DCT coefficient, which JPEG will use in the succeeding entropy coding. Quantization step is the main source for loss in JPEG compression. The entries of Q of u, v tend to have larger values towards the lower right corner. The table is used to maximize the compression ratio while minimizing the losses. This aims to introduce more loss at the higher spatial frequencies. Using DCT, there is very little loss of information during the DCT phase. The losses are due to the use of fixed point arithmetic. The main source of information loss occurs during the quantization and entropy encoding stages, where the compression takes place. The human eye responds primarily to the DC coefficient and the low frequency coefficients. The higher frequency coefficients below a certain threshold will not be detected by the human eye. This property is exploited by dropping the spatial frequency coefficient in the transformed matrix. Dropped coefficients cannot be retrieved during decoding. In addition to classifying the spatial frequency components, the quantization process aims to reduce the size of DC and AC coefficients so that less bandwidth is required for their transmission by using a divisor. The sensitivity of the eye varies with spatial frequency, and hence the amplitude threshold below which the eye will detect a particular frequency also varies. The threshold values vary for each of the 64 DCT coefficients, and these are held in a 2D matrix known as the quantization table with the threshold value to be used. The choice of threshold value is a compromise between the level of compression that is required and the resulting amount of information loss that is acceptable. JPEG standard has two quantization tables for the luminance and the chrominance coefficients. However, customized tables are allowed and can be sent with the compressed image. The luminance quantization table can now be seen on the screen, followed by the chrominance quantization table. From the quantization table and the DCT and quantization coefficients, a number of observations can be made. The computation of the quantized coefficients involving rounding the quotients to the nearest integer value. The threshold values quantization table used increase in magnitude with increasing spatial frequency. The DC coefficient in the transform matrix is the largest. Many of the higher frequency coefficients are 0. Vectoring. The entropy encoding operates on a one-dimensional string of values known as vectors. However, the output of the quantization is a 2D matrix, and hence this has to be represented in a 1D form. This is known as vectoring. Differential encoding. In this section, only the difference in magnitude of the DC coefficient in a quantized block relative to the value in the preceding block is encoded. This will reduce the number of bits required to encode a large magnitude. The difference values are then encoded in the form SSS, value. SSS indicates the number of bits needed and actual bits that represent the value. For example, if the sequence of DC coefficients in consecutive quantized block were 12, 13, 11, 11, 10, then the difference values will be 12, 1, minus 2, 0, minus 1, and so on. Vectoring using zigzag. The zag scan can now be seen on the screen. In order to exploit the presence of the large number of zeros in the quantized matrix, a zigzag of the matrix is used. Run length coding. The remaining 63 values in the vector are the AC coefficients. Because of the large number of zeros in the AC coefficients, they are encoded as string of pairs of values. Each pair is made up of skip, value, where skip is the number of zeros in the run and value is the next non-zero coefficient. The above will be encoded as 0, 6, 0, 7, 0, 3, 0, 3, 0, 3, 0, 2, 0, 2, 0, 2, 0, 2, and 0, 0. Final pair indicates the end of the string for this block. Huffman coding. Significant levels of compression can be obtained by replacing long strings of binary digits by a string of much shorter code words. The length of each code word is a function of its relative frequency of occurrence. Normally, a table of code words is used with a set of code words pre-computed using the Huffman coding algorithm. Frame building. In order for the remote computer to interpret fields and tables that make up the bit stream, it is necessary to delimit each field and set of table values in a defined way. The JPEG standard includes a definition of the structure of the total bit stream relating to a particular image/picture. This is known as a frame. The role of the frame builder is to encapsulate all the information relating to an encoded image or picture. At the top level, the complete frame plus header is encapsulated between a start of frame and an end of frame delimiter, which allows the receiver to determine the start and the end of all the information relating to a complete image. The frame header contains a number of fields: the overall width and height of the image in pixels, the number and type of components, CLUT, RGB, YCBCR, the digitization format used, 4:2:2, 4:2:0, etc. At the next level, a frame consists of a number of components, each of which is known as a scan. The level 2 header contains fields that include the identity of the components/scan, the number of bits used to digitize each component, the quantization table values that have been used to encode each component. Each scan comprises one or more segments, each of which can contain a group of 8 by 8 blocks preceded by a header. This contains a set of Huffman code words for each block. JPEG decoder. A JPEG decoder is made up of a number of stages, which are simply the corresponding decoder sections of those used in the encoder. The frame decoder first identifies the encoded bit stream and its associated control information and tables within the various headers. It then loads the contents of each table into a related table and passes the control information to the image builder. Then the Huffman decoder carries out the decompression operation using preloaded or the default tables of code words. The two decompressed streams containing the DC and AC coefficients of each block are then passed to the differential and run length decoders. The resulting matrix of values is then dequantized using either the default or the preloaded values in the quantization table. Each resulting block of 8 by 8 spatial frequency coefficient is passed in turn to the inverse DCT, which in turn transforms it back to the spatial form. The image builder then reconstructs the image from these blocks using the control information passed to it by the frame decoder. JPEG modes. JPEG is divided into 4 modes. These are sequential mode, lossless mode, progressive mode, hierarchical mode. Sequential mode. Each image is encoded in a single left-to-right, top-to-bottom scan. The technique we have been discussing so far is an example of such a mode, also referred to as the baseline sequential mode. It supports only 8-bit images as opposed to 12-bit images as described before. Characteristics of lossless mode. It is truly lossless. It is a predictive coding mechanism as opposed to the baseline mechanism, which is based on DCT and quantization, the source of the loss. Here is a simple block diagram of the technique. Predictive difference. For each pixel, a predictor, 1 of 7 possible, is used that best predicts the value contained in the pixel as a combination of up to 3 neighboring pixels. The difference between the predicted value and the actual value, x, contained in the pixel is used as the predictive difference to represent the pixel. The predictor along with the predictive difference are encoded in the pixel's content. The series of pixel values are encoded using Huffman coding. Referring to the expression on screen, the very first pixel in location 0, 0 will always use itself. Pixels at first row always use P1. Pixels at first column always use P2. Best prediction always depends on pixels. Progressive mode. It allows a coarse version of an image to be transmitted at a low rate, which is then progressively improved over subsequent transmissions. Spectral selection. Send DC component and first few AC coefficients first, then gradually some more ACs. Successive approximation. All the DCT components are sent few bits at a time. For example, send N1, say 4 bits, starting with MSB, of all pixels in the first scan. The next N2, say 1, bits of all pixels in the second, and so on. Hierarchical mode. Used primarily to support multiple resolutions of the same image, which can be chosen depending on the target's capabilities. The figure here shows a description of how a 3-level hierarchical encoder/decoder works. It has 3 lossless modes and 1 lossy mode. Sequential baseline encoding. Encode in 1 scan. Input and output data precision is limited to 8 bits, while quantized DCT values are restricted to 11 bits. Progressive, hierarchical encoding, lossless encoding can achieve compression ratios up to 20:1 without noticeable reduction in image quality. The JPEG specification defines a minimal subset of the standard called baseline JPEG, which all JPEG-aware applications are required to support. This baseline uses an encoding scheme based on the discrete cosine transform DCT to achieve compression. DCT is a generic name for a class of operations identified and published some years ago. DCT-based algorithms have since made their way into various compression methods. DCT-based encoding algorithms are always lossy by nature. DCT algorithms are capable of achieving a high degree of compression with only minimal loss of data. This scheme is effective only for compressing continuous tone images in which the differences between adjacent pixels are usually small. In practice, JPEG works well only on images with depths of at least 4 or 5 bits per color channel. The baseline standard actually specifies 8 bits per input sample. Data of lesser bit depth can be handled by scaling it up to 8 bits per sample, but the results will be bad for low bit depth source data because of the large jumps between adjacent pixel values. For similar reasons, color map source data does not work very well, especially if the image has been dithered. JPEG compression and decompression. The JPEG compression scheme is divided into the following stages. Transform the image into an optimal color space, downsample chrominance components by averaging groups of pixels together, apply a discrete cosine transform DCT to blocks of pixels, thus removing redundant image data. Quantize each block of DCT coefficients using weighting functions optimized for the human eye. Encode the resulting coefficients image data using Huffman variable word length algorithm to tendencies in the coefficients. Decompression, the reverse process of compression. JBIG compression, standard for bilevel compression. By segmenting an image to overlapping and non-overlapping regions of text, half-tone, and generic content, and compression techniques specially optimized for each type of content. The main features of JBIG are lossless compression of 1 bit per pixel image data, ability to encode individual bit planes of multiple bit pixels, progressive or sequential encoding of image data. Bilevel images contain only 2 colors and are stored using a single bit per pixel black and white image. Typical bilevel compression algorithms encode only a single scan line at a time using a run length encoding technique. Such algorithms are referred to as 1D encoding methods. 2D encoding methods encode runs of pixels by describing the differences between the pixel values in the current and the previous scan lines. JBIG encodes redundant image data by comparing a pixel in a scan line with a set of pixels already scanned by the encoder. These additional pixels are called a template, and they form a single map of the pattern of pixels that surround the pixel that is being encoded. The values of these pixels are used to identify redundant patterns in the image data. These patterns are then compressed using an adaptive arithmetic compression coder. The adaptive nature of templates allows the color of the pixel values being encoded to be predicted with a high degree of success. For grayscale images with half-toning, compression ratios are increased by as much as 80% over non-adaptive methods. Although designed primarily as a method for compressing bilevel image data, JBIG is capable of compressing color or grayscale images with a depth of up to 255 bits per pixel. Such multi-bit pixel images are compressed by bit plane rather than by pixel. For example, an 8-bit image compressed using JBIG would be encoded into 8 separable bit planes. This type of encoding may be used as an alternative to lossless JPEG. JBIG has been found to produce better compression results than lossless JPEG using the Q coder on images with 2 to 5 bits per pixel and to produce identical results on image data with pixels 6 to 8 bits in depth. It is recommended that each bit plane be pre-processed with gray coding algorithm to normalize the changes between adjacent byte values in the image data. This process increases the efficiency of the JBIG encoder. JBIG images may be encoded sequentially or progressively. Sequentially encoded images are stored in a single layer at full resolution and without other lower resolution images being stored in the same data stream. This sequential JBIG image is equivalent in function and application to a G4 image. Such an image is decoded in a single pass and has at least as good a compression ratio as G4. Progressively encoded images start with the highest resolution image and end with the lowest. The high resolution image is stored in a separate layer and is then used to produce a lower resolution image, also stored in its own layer. Each layer after the first layer is called a resolution doubling. An image with 3 layers is said to have 2 doublings. There is no imposed limit to the number of doublings that may be encoded. For example, a 1200 dpi image may be encoded as 1 layer, 1200 dpi, 3 layers 1200, 600 and 300 dpi, or 5 layers 1200, 600, 300, 150 and 75 dpi. The lowest resolution is determined by whatever is considered useful. Even a 10 dpi image, though not legible, is still useful as an icon. Progressive decoding is the opposite process, with the lowest resolution image being decoded first, followed by increased resolutions of the image until the full resolution is achieved. This technique has the advantage of allowing data to appear immediately on the output device. Only data up to the appropriate resolution of the output device need be decoded and sent. Both sequential and progressive JBIG encoding are completely compatible. Images compressed using sequential encoding are readable by progressive JBIG decoders. Sequential JBIG decoders are only capable of reading the first, lowest resolution layer within a progressively encoded JBIG image. Many applications that utilize JBIG may only have use for sequential encoding and decoding, especially those used for facsimile transmission. It is therefore possible to implement a simplified JBIG algorithm that encodes only the first layer in a JBIG data stream. Such encoders produce a valid JBIG encoded data stream that is readable by all JBIG decoders. Progressive encoding does not add much more data to the JBIG data stream than does sequential encoding, but it does have greater memory requirements. Because a lower resolution image is encoded from data of the next higher resolution image, and vice versa when decoding, a frame buffer must be used to store image data that are being used as a reference. Error-free and lossy compression. Lossy compression. Lossy encoding is based on the concept of compromising the accuracy of reconstructed image in exchange for increased compression. Lossy encoding technique is capable of reproducible and recognizable monochrome images from data that have been compressed more than 100:1 and images that are virtually indistinguishable from the original at 10:1 to 50:1. The block diagram for a lossy compression is now seen. Lossy compression methods, spatial domain method, transform coding. Lossy predictive coding transmits the difference between estimate of future samples and sample itself. Methods: delta modulation, DPCM, adaptive predictive coding, differential frame coding. Lossy predictive encoder technique used to get compressed image. The related block diagram can now be seen. Lossy predictive decoder technique used to get decompressed image which is same as input image, as depicted in the block diagram. The decoder uses error stream to reconstruct an approximation of the original signal. 1. The predictor is initialized using the first sample. 2. The received error is added to the predictor result. Delta modulation. It is an analog to digital and digital to analog signal conversion technique used for transmission of voice information where quality is not of primary importance. Differential pulse code modulation (DPCM). Differential pulse code modulation (DPCM) is a signal encoder that uses the baseline of pulse code modulation (PCM) but adds some functionalities based on the prediction of the samples of the image. The encoder and decoder block diagrams for the differential pulse code modulation is shown. The input can be analog or a digital image. The reconstruction error equals quantization error. The concerned equation is shown. For a linear predictor, the DPCM coder is equivalent to where the linear DPCM decoder, thus error is filtered by 1 divided by 1 minus p of Wx, Wy. Signal distortions due to intra-frame DPCM coding. Granular noise, random noise in flat areas of the picture. Edge busyness, jittery appearance of edges for video. Slope overload, blur of high contrast edges, Moire pattern in periodic structure. Prediction error for different prediction followed by a 512 by 512 bit monochrome image. The prediction error equations can now be seen. This is also shown for different prediction errors. A typical quantization function. T equals Q of S, where Q is an odd function. This graph shows the reconstruction and decision levels of quantization function. The optimal quantization equations can now be seen. Table for mean square error summary. The following is a table constructed for a unit variance distribution for the reconstruction and decision levels for the case of pi equals 1, which are obtained by multiplying tabulated values by standard deviation or probability density function. Transform coding. It is used to convert the data into the form where compression is easier. This transformation will transform the pixels which are correlated into a representation where they are decorrelated. The new values are usually smaller on average than the original values. The net effect is to reduce the redundancy of representation. A linear reversible transform is used to map the images into a set of transform coefficients, which are then quantized and coded. The below image for transform encoding. Transform encoding is used to produce compressed images. Original image is divided into n by n sub-images. Then the sub-images are sampled by forward transform. After sampling process, image will be digitized using quantization process. Source coding is used to reduce redundancy in images. To get decompressed image, the above process will be reversed, as is now seen. The transform coding equations can now be seen. This is now shown for two different cases. Forward kernel is separable and forward kernel is symmetric. The discrete Fourier transform DFT equations can be seen on screen, followed by Walsh-Hadamard transform WHT. The Walsh-Hadamard basis function is also shown in the diagram now. Discrete cosine transformation DCT equations follow. The related diagram can now be seen. The steps involved in DCT are dividing the images into sub-images of 8 by 8, representing each sub-image by using one of the transform, truncating 50% of coefficients, taking the inverse transform for truncated coefficients. The advantages of DCT are: it's implemented in a single integrated circuit, packing the most information into the fewest coefficients, minimizing the block-like appearance. The implicit periodicity can now be seen. The screen now shows the sub-image size selection, truncation 75% of coefficients. The thresholding bit allocation method can now be seen on the screen. The characteristics of zonal coding are fixed number of bits and coefficients. Coefficients are normalized by the standard deviation and uniformly quantized. Fixed number of bits distributed among coefficients unequally. A quantizer, such as an optimal Lloyd max, is designed for each of the coefficients. DC function is modeled by Rayleigh density function. The remaining functions are modeled by Laplacian or Gaussian. The threshold coding characteristics are 1. Single global threshold. 2. Different threshold for each sub-image. 3. Threshold can be varied as a function of location of each of the coefficients. Transform coding bit allocation. Threshold quantization curve and normalization metrics are given below. A. Thresholding quantization. B. Normalization metrics. Image compression fundamentals. Process of reducing the amount of data required to represent a given quantity of information. Represents that irrelevant or repealed information said to contain redundant data. Relative redundancy data are represented by R and bits represented by B. R equals 1 minus 1 by C, where C is called as compression ratio. C equals B by B dash. Redundancy in data representation of an information provides no relevant information or repeats a stated information. Let N1 and N2 be the data representation. Then the relative data redundancy R of N1 is defined as R equals 1 minus 1 by C, where C equals N1 by N2. Redundancy in digital images. Other criteria for determining the suitability of a compression method for certain applications are the time and memory needed for the attained compression ratio, the time and memory needed for decompression. Three types of data redundancy are used to design data compression methods. 1. Coding. 2. Interpixel or interframe for a series of images. 3. Application-specific, for example, psychovisual for the viewing of images by people. Coding redundancy usually appears as a result of the uniform representation of each pixel. Spatial/temporal redundancy, because the adjacent pixels tend to have similarity in practice. Irrelevant information. Image contains information which are ignored by the human visual system. Coding redundancy. Assume the discrete random variable for Rk in the interval 0, 1 that represents the gray levels. Each Rk occurs with probability Pk. If the number of bits used to represent each value of Rk by LRk, then the equation assumes the form as shown on the screen. The average code bits are assigned to the gray level values. The length of the code should be inverse proportional to its probability occurrence. Examples of variable length coding is given in the table as seen. Spatial/temporal redundancy. Internal correlation between pixels result from respective autocorrelation, structural relationship, geometric relationship. The value of a pixel can be reasonably predicted from the values of its neighbors. To reduce the interpixel redundancies in an image, the 2D array is transformed, mapped. Irrelevant information and psycho-irrelevant information and psychovisual redundancy. The brightness of a region depends on other factors than the light reflection. The perceived intensity of the eye is limited as nonlinear. Certain information has less relative importance than other information in normal visual processing. In general, observer searches for distinguishing features such as edges and textural regions. Measuring information. A random event that occurs with probability P of E is said to contain I of E probability information, where I of E is defined as shown on the screen. Where P of E equals 1 contain no information, P of E equals half requires 1 bit of information. For a source of events A0, A1, A2 going up to AK with associated probability P of A0, P of A1, P of A2 going up to P of AK, the average information per source entropy is as shown on the screen. For image, we use a normalized histogram to generate the source of probability, which leads to entropy as shown. Fidelity criteria. Objective fidelity criteria. The information loss can be expressed as a function of the encoded and decoded images. For image I, x, y and its decoded approximation I dash x, y. For any value of x and y, the error E of x, y could be defined as shown. The mean square error signal to noise ratio SNRMS is the image compression system block diagram is shown on the screen.